Alright, so this first review question relating to infrared spectroscopy. It's a great question for us to take a look at. And we're given a formula so we know what elements are involved in this compound, and we're told that there is a signal at 1720. So anytime I see a signal between 1650 and 1750 in the IR, that tells me that I've got a carbon-oxygen double bond in my structure. Specifically, the stretching of that bond is what absorbs energy in that frequency. So that does tell me that my oxygen has to be bonded to a carbon through a double bond. It's not going to have a hydrogen on it. Assuming we have a stable structure here, we're not going to have any formal charge. So then what we talked about at the end last time as well was, if you have a formula, just draw a structure and see how many hydrogens it would take to saturate it. So if I've got 4 carbons, 1, 2, 3, 4, and an oxygen, I'll just put that oxygen anywhere for now. How many hydrogens would it take to saturate the structure? Well, if it were saturated, I would have 1 on the oxygen. So it'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if it takes 10 hydrogens to saturate it, and I only have 8, that's 1 degree of unsaturation. And if the IR is telling me that I have a carbon-oxygen double bond, that accounts for my degree of unsaturation. So that means I shouldn't have any other degrees of unsaturation if this is going to match up with this given formula. So that means I've got 4 carbons and a CO double bond. So then I can start drawing isomers that match with that. 4 carbons, maybe I have a CO double bond here on the end. Or another possible structure, 4 carbons with the CO double bond here. What if I drew it like this? Is that a third possible structure? Well, not really. This molecule can be rotated around and superimposed directly on this one. So there's no point in me drawing both of them if they're the same structure. I'm just trying to draw all the different possible isomers for this formula that would match and give me this IR signal. So what else is there? Can I do a 4-membered ring with a double bond? Well, that wouldn't match the formula because the double bond is 1 degree of unsaturation and a ring is another degree of unsaturation. If I do both and I have 2 degrees of unsaturation, I'm only going to have 6 hydrogens instead of 8. And that would be true when I try to draw them in and realize that there are only 6 positions for me to put hydrogen. So that one doesn't match the formula, even though it matches potentially what I'm seeing here in the IR spectrum. So I could look at branching, right? So I don't have to have my carbons in an extended chain. If I have 4 carbons, I could do branching. So then I could put the CO double bond here. 1, 2, 3, 4 carbons. It's 3, 6, 7, 8 hydrogens. And with that branching, that's really all I can do, because once I do the branching, it's not like I can put the CO double bond there. I'd have a 5-bonded carbon, so that also would not make sense. So it looks like there are only 3 possible structures that could give both this formula with only 1 degree of unsaturation, and also includes that degree of unsaturation as a CO double bond to match the IR peak there at 1700. Questions about that one? Alright, so then the next one is similar, but here we have some different information. We have an especially broad signal between 32 and 3600. So that tells me that I probably have an OH stretch. the oxygen-hydrogen bond stretching requires a fairly high energy to cause that stretch, and this is on the high energy side of the scale. I also have a very broad signal, which indicates that it's likely hydrogen bonding with another molecule. So there's probably an R group here, but the large partial positive, partial negative, it makes the covalent bond a little weaker in some of the molecules that are engaged in hydrogen bonding, but hydrogen bonds are constantly breaking and forming. So it's not like every molecule is going to have the exact same environment. Some will have strong hydrogen bonds and a weaker covalent bond. Some might not have hydrogen bonds and they'll have a stronger covalent bond. So some of the molecules will give an OH stretch for the weaker covalent bond in the lower energy side of that, and other molecules will give a stretch in the higher energy side, and some will be in between. So that's why I see one broad signal, because I've got thousands and millions and billions of molecules, each with an OH that requires a slightly different amount of energy to stretch. So I see those all stacked next to one another, and it gives one broad signal when they all kind of add together. And it says it does not contain any signals in the area between 1650 and 1750, so no carbon-oxygen double bond. And when I look at the formula, it's the same formula we had in the last problem, so I have 1 degree of unsaturation. So in this case, if I have 4 carbons, I'm trying to draw some structures here, and I expect to have an OH, if I don't put any double bonds or rings, then I won't have 8 hydrogens. I'll have 10. 2, 4, 6, 7, 8, 9, 10 total hydrogens. So to get my structure to match the formula, I do need a double bond somewhere or a ring. So since the question doesn't tell me anything about the CH stretching region, which is around 3000, I don't know if I have only CH stretching on sp3 hybridized carbons or if there's CH stretching on sp2 hybridized carbons. So I could have a double bond here in my structure somewhere. So if I have a straight chain molecule, I could have the double bond here. I could have it here. Or I could have it there. Each one of those would give the OH stretch and match the C4H8O formula that was given. It doesn't have to be a straight chain molecule. It could have some branching. The OH doesn't have to be on the end of the structure. So even before I get to branching, I could have put the OH here. And so that means I could have the double bond here, here, or here. So that's 3 more options that are all slightly different from one another. So there are really 6 different isomers I can draw here that have the carbons in a straight chain, and I haven't even looked at branching yet. So if I do a little branching, 4 carbons with some branching instead of all extended, here I could put the OH on the end. And so that means I could have the double bond here, or I could have the double bond here. I need the double bond, as we said, to account for that 1 degree of unsaturation and match up with the formula. Right, so I don't have to count the hydrogens on every formula and make sure it matches up. As long as all my structures have 1 degree of unsaturation and 4 carbons and 1 oxygen, then it should match the formula. If I have branching and maybe the OH is on the central carbon, so that's not going to work because there's no way for me to make a stable structure that also has a degree of unsaturation here. When I put the oxygen on that central carbon, I can't make a double bond at any one of these sites, or I'll have a 5 bonded carbon, so that's not an option. There's one more structure that I could draw, and that would be a ring. So in this case, a ring accounts for that 1 degree of unsaturation, and now if I have an OH attached to it at any one of those 4 positions, it's going to be the equivalent, whichever carbon I attach the OH to. But that's going to have then a total of 8 hydrogens in the structure. So here there are 9 different structures that I could come up with. I may be missing 1 or 2, but that's basically how you would think about that. You would exhaust every possible way of connecting the atoms. Actually, no. Now I'm thinking of more because there are stereoisomers. So one molecule that has this connectivity, another molecule could be very similar but have the OH pointing away. And since that's a chiral center, those two structures are unique. They're not identical. But that looks like the only one that has a chiral center in it. So that adds one more possible isomer that could have produced both that IR peak around 3500, 3400, as well as matching the formula for the structure. Any questions about any of those?
I have a question. Didn't you also have a 3-membered ring?
Yeah, very good. Didn't think of that. Yeah, so it's unlikely in an exam question I would ask you to come up with all the possible structures because it's easy to overlook one or two ways of drawing new structures, but that's true. So the 3-membered ring would definitely be possible. It's even more unstable than the 4-membered ring due to the extra angle strain and the torsional strain that the 4-membered ring can avoid by doing a little bit of a puckering that we talked about way back when. But with the 3-membered ring, I could put a carbon here, and then I could put the OH there, or I could put the OH here, or I could put the OH on one of these other carbons. And when I put it there, that creates a chiral center now, which isn't true for either of the other two structures. So that means I actually have two more. And actually, this is a chiral center now too. So that creates actually a few more stereoisomers where the OH and methyl group are on the same side or on opposite sides. So then I have to really consider whether these are all spatially different or not. And that might be more easy to see with the model kit, but let's see this structure here where the two groups are pointing away. If I flip that over like a pancake, it'll look exactly like this one. So these two are not unique, so I would only draw one of them. They're identical by flipping the structure over and rotating it around. So I wouldn't want both of those. In the case of this one that I'll label 1 and this one I'll label 2, are these two identical or are they unique? So if I flip the structure over and rotate it around, if I flip it over, the solid wedge will become a dash wedge. So let's just talk about that first. So if I flip that over like a pancake, OH would be up here and the methyl would be down there. So is that going to be superimposable upon compound 2? I don't think so. Looks like they're different. But the best way to check that would be with a model to show that once you make both of these compounds, they're not superimposable upon one another. So there are a lot of different structures you could draw with this one, including the 3 and 4-membered ring. Nice work with that, Kristen. Any other questions or comments on that one? Alright, so we're going to talk about NMR today. We're going to talk about how NMR works and a little bit about how to interpret NMR spectra. And then we're going to continue that on Thursday. There's a lot of information in an NMR. A lot more than you get in an IR. We talked about IR. We said you can tell what some of the bonds are that are present in the structure, but as we just showed here, the IR doesn't really give you much information about how everything's connected. Almost every one of these is going to give me a pretty similar IR spectra. I'm going to get the OH stretch. I'm going to get a CH stretch on an sp2 hybridized carbon. I'll get a CH stretch on an sp3 hybridized carbon. So these ring structures would be a little different. They would only give me CH stretches on sp3 hybridized carbons, which come below 3000, whereas the CH stretch on an sp2 hybridized carbon comes above 3000. So there are some differences here, but a lot of these different isomers I can't really distinguish by IR. When we look at NMR and we go through all the detail, you'll see that NMR can distinguish between isomers much more readily. And if you look closely at the NMR and are able to interpret all the information that's in there, you can really pretty strongly determine the identity of a substance. And that also obviously relates to the goal of Lab 7. So NMR is a type of spectroscopy. So just like IR, we're using light to interact with the sample. And then we're observing what happens to the light upon interacting with the sample. It's not going to break down the sample or change it chemically. It's just going to interact with it. In the case of IR, the light gets absorbed. The light hits the molecule, causes the molecule to start stretching or bending, and the light's no longer there because now that energy that was in the form of light is now in the form of kinetic energy, vibration of the bonds. In NMR, it's going to be similar, except in NMR, the light is going to hit the sample, cause it to get excited, and then it's going to relax back down and emit some energy that the instrument will detect. So we'll be looking, instead of the energy that's absorbed in infrared, we'll be looking at energy that's emitted in the NMR, and that will give you a lot more detail about that as we go through here. So this is probably the most powerful way of gaining structural information about organic compounds. It's definitely the most common way you would identify a substance or verify the structure of a substance, right? So in the case of Lab 6, where we're trying to make this compound, did you make it? Well, probably the easiest way is to put your product in the NMR tube and see if the NMR shows peaks that are indicating this particular structure, and some of you were able to see that for your Lab 6 samples. So we're going to talk in detail about how to interpret NMR after we talk about what the instrument does and how it works a little bit. So in NMR, the N stands for nuclear, and that's because we're looking at energy changes that occur in the nucleus of an atom. And since we're in organic chemistry, we're going to be looking at carbon and hydrogen nuclei. And what we're going to find is, depending on what else is bonded to a carbon, not just what's bonded to it directly, maybe it's another carbon, maybe it's an oxygen, but what might be also bonded nearby. Any other atoms and the way that they're connected structurally to the carbon is going to affect the quantity of energy that this carbon absorbs and then re-emits. So we're going to see how the structural features of the molecule affect each individual nucleus and how that affects its interaction with light energy. So the structural connectivity of the molecule affects how light interacts with the structure, and that allows us to get information about each nucleus in the molecule and what the structure of the molecule looks like. So it turns out that the protons and neutrons in the nucleus, they behave as if they're little spinning particles. So we don't know if they're actually spinning or not, which is why I put spinning here in quotes this morning. But they behave as if they're spinning, and that's because spinning charges create a magnetic field. So these particles in the nucleus, when they're spinning, it creates a magnetic field, and that magnetic field we're going to take advantage of by placing them in the NMR, and the M stands for magnetic. So the NMR instrument has a magnetic field, and when we put our sample in a magnetic field, if it has carbon or hydrogen, or if we have a nice NMR that can analyze for other elements, those will also be possible to look at. We're just going to focus on carbon and hydrogen. The carbon and hydrogen nuclei interact with the magnetic field in the instrument because they have a magnetic field. So only nuclei that have this spinning charge creating a magnetic moment will be observable in the NMR, but since that includes the nuclei that we're really interested in, that's convenient for us. We know that almost every hydrogen has a single proton and no neutron, so it has a mass of 1, so hydrogen will definitely be something that will be affected by the magnetic field in the NMR instrument. And for carbon, it's really carbon 13. So most carbons have a mass of 12, but the instrument is only going to look at carbon 13. So carbon 13 only makes up about 1% of naturally occurring carbon atoms. So a lot of the atoms in your molecule won't give any signal, but if you have enough of a sample where at least some of the molecules have a carbon 13 at one or another position, then you should get a signal for every carbon in the structure, which is typically what you see unless you have a very small amount of sample. So this magnetic moment for these individual atoms, so this is a property of the individual nuclei. Each nucleus, hydrogen or carbon, creates a magnetic moment or a magnetic field that's going to interact with the external magnetic field in the instrument, and that's going to allow us to look at the molecules in detail, as we'll see going through here. So it's just a picture that shows how if I have a spinning particle, it creates a magnetic field perpendicular to the axis of the spin. And so these little arrows here represent that. So if I just have my sample on the bench in the lab, each individual nucleus, its magnetic field is positioned in some random direction. Right? So these arrows, want to make clear, they don't represent the position of a molecule in space. Right? So we're not talking about the molecule being aligned. We're talking about the magnetic field created by the hydrogen and carbon atoms aligning randomly. Once that sample is placed in the instrument, so the blue lines here represent the magnetic field created by the instrument. So this instrument will have a big magnet, and that magnet will cause an attraction to the hydrogen or carbon atoms, and they will either align with or against the magnetic field of the instrument. So they're not random anymore. Without the magnetic field, they're all just pointing randomly, indicating that there's no alignment of any of the individual atoms' magnetic fields in any way. But once we put those in the instrument and they align with or against the instrument, now I've got two different states. Each hydrogen, so if we're looking at proton NMR, each hydrogen atom has a magnetic field, and so it's not like the molecule is moving in space to align in any way, but the magnetic field of that hydrogen can either align with or in the same direction as the instrument's magnetic field or against. And the way it turns out is these two states are not equal in energy, and that is what we're going to take advantage of. So if the hydrogen atom's magnetic field aligns with the external magnetic field, it's a little bit lower in energy. If it lines up against the magnetic field, it's a little bit higher in energy. If it were to line up in some other direction, it would be much higher in energy. So we really don't see that. We see two different states, a lower energy state and a higher energy state. And the difference in energy is a very small difference in energy. And we know that because if I have my hydrogen atom aligned in one direction and I hit it with large quantities of energy, I don't see anything happening. I only see this effect in the NMR when radio waves are used. So when we said light comes in a variety of different forms, The electromagnetic spectrum goes from gamma rays, which have, gamma rays have really short lengths, so they're very high in energy, all the way to the other end, which is radio waves. And radio waves have very long wavelengths, so they're much lower in energy. So that the energy difference is small, then we would use a low energy form of radiation to try to excite these lower energy spin states up to the higher states. And so that's what happens in the instrument. So you put your sample in the instrument. Each hydrogen or carbon atom aligns with or against the magnetic field created by the instrument. And then it's hit with radio waves that have just the right amount of energy to excite the hydrogens from one spin state to another spin state. So the ones that are aligned up with the magnetic field, if the radio waves hit those, they'll flip. And they will become aligned against the magnetic field. So we're changing the energy of those hydrogen atoms just a little bit with a very small quantity of energy associated with this light. If I use a stronger applied magnetic field in the instrument, then there's an even bigger difference between the two possible spin states. So it'll take a larger quantity of energy to do the excitation. So there's also a relationship there. So once the hydrogen or carbon nuclei spin and create a magnetic field against the applied magnetic field that's higher in energy, then the instrument stops hitting it with radio waves, and eventually they relax back down. So these beta ones are higher in energy. They'll flip back to the alpha. And when it goes from higher energy beta to lower energy alpha, after it's been excited, that energy is then released in the surroundings. And the instrument detects it. And so that's the signal that the instrument measures and plots for you to interpret to tell you what the structure of the compound is. So in essence, the magnetic field is necessary to create the difference in energy between the two ways the atoms can align, and then the radio waves are used to excite the lower energy alignment to higher energy alignment, and then when it relaxes back down, it releases energy that's measured. Right? So that's the gist, the basic gist of how the experiment works. So if I have a structure, let's say I've got ethanol just for the sake of argument, and in the ethanol I've got a number of different hydrogens. So if we take a look at the 2 hydrogens here versus the 3 over here, it turns out that if the hydrogen atoms are closer to something electronegative like the oxygen, right? So the oxygen's pulling these electrons away through induction. It's creating a large partial positive here. That attracts the electrons away from these hydrogens, so they carry large partial positives. So when the electrons are not effectively shared with the atom because they're pulled away by a highly electronegative atom, those elements are called de-shielded. Over here, this hydrogen's not as de-shielded because they're farther away from the oxygen, right? So when the oxygen pulls electrons away to create a partial positive here, that carbon will pull electrons away from this carbon, creating a small partial positive there, and I'll pull electrons away. So I'll get some tiny partial positives on these hydrogens here, but they'll be very minimal. For the most part, the sigma bond here is shared pretty evenly over both the carbon and the hydrogen. So these hydrogens are more shielded, which means they have more electron density around them. And what that shielded means is they're not as affected by the magnetic field. So what we're saying is the hydrogen atoms start off aligned with the magnetic field for the most part because that's lower in energy. When the radio waves hit them, the radio waves have to have the exact amount of energy to be absorbed and to cause the spin to switch to the beta spin, which is higher in energy. But if the hydrogen has a lot of electron density around it, it's not going to be as affected by the magnetic field. And so that's what we see when we talk about shielding. So if I have a hydrogen nucleus, a proton, and it's surrounded by lots of electrons, that means that the magnetic field doesn't affect it as much. And then there's going to be a smaller difference in energy between the alpha and beta states. So when this hydrogen absorbs radio waves and changes its spin state to the beta state, it won't be that high in energy. And so when it relaxes back down to the alpha state, it will release less energy. So I see lower quantities of energy released for shielded protons. And when I see lower quantities of energy released, that tells me about the structure. So I can tell how much energy should normally be released when a proton's one atom away from an oxygen versus two atoms away. And so there are differences, subtle differences based on where the atom is in the structure and what's around it that will determine the quantity of energy that it absorbs because of how the electron density around it affects the energy difference when it's aligned one way with the magnetic field versus in an opposite direction against the magnetic field. So as we said, radio wave energy is used to excite the nuclei from the lower energy alignment with the magnetic field to the higher energy alignment against the magnetic field. When those spin states are flipped to their higher energy state, that's called resonance. And unfortunately, this is a different meaning from what we've already learned the word resonance means. So there are two different, totally different, distinct meanings for the word resonance. So the R in NMR stands for resonance. It's not the type of resonance we've talked about where electrons can be spread out over multiple atoms by being shared in overlapping p orbitals over multiple atoms to stabilize the structure. That's the type of resonance we've been talking about throughout the semester. This is a different thing entirely. It refers to the hydrogen nuclei or carbon nuclei existing with this higher energy spin state. So to create this situation, you have to put the atoms in an external magnetic field and then hit them with radio wave energy to cause their spin states to be excited or in resonance. And then when those excited spin states relax back down to the normal lower energy spin state, that energy is emitted, and depending on the quantity of energy, that gives us information about how many hydrogens there are in the structure, how shielded they are with electron density versus deshielded by electronegative atoms, and we can start to piece together the structure of the molecule based on the information we get from the NMR. So that's the basic idea here that we're going to explain as we continue to go through. So, as we were saying, the more strong the magnetic field is in the instrument, the more of an energy difference there is. Right? So, if you have a sample with lots of different hydrogens that all have pretty similar environments and you want to tell the difference between them, you need a really strong magnet. And don't worry about this unit, just recognize that this represents a unit of how strong the magnet is. If I have a really strong magnet, I have a bigger energy difference, right? Because it's going to be really stable if the atoms align with that magnet and much more unstable if they align against it. Right? So these arrows are not electrons. They're the direction of the magnetic field created by the nuclear, the particles in the nucleus. So if I have a very weak magnet, imagine something really weak, and there's only a small difference in energy between those two alignments, then if I have one type of hydrogen versus another, the energy difference that they might give would be pretty small. It would be hard to tell the difference. So the stronger the magnet, the more obvious it is when you have different types of hydrogens. So that's one of the disadvantages we have here at LCCC, is that our NMR instrument does not have a very strong magnet. So our peaks aren't as sharp. We can't tell the difference between really similar hydrogens very readily. But if you go to big research institutions, they have entire rooms filled with a magnet that's really strong and big, and that will allow them to analyze much more complicated structures where they can tell the difference between hydrogens that have pretty similar environments that aren't exactly the same. And in those situations, for the magnet to reach its highest strength, there needs to be a really high current passed through superconducting material, and that only works at a really low temperatures. And so that's why we don't have that, because all of that is really expensive to undertake, and we don't have the research needs for it either. So it'd be silly for us to spend the money to put something like that together. So the way most of these instruments work is you put the sample in your magnetic field, and then it hits the sample with radio energy of all the different wavelengths in the region that might cause the hydrogen atoms to switch their spin states. When the atoms are excited, they align against the magnetic field, and then they realign with the magnetic field. Upon relaxing, they emit energy, as we said, and all the different hydrogens are emitting energy at the same time. All that energy emitted is detected, and that creates a signal called a free induction decay. Don't worry about that terminology. That signal then is treated mathematically with something called Fourier transform, which we're not going to get into the details associated with that. That's very mathematical. But basically, that mathematical treatment then separates all the individual signals. So the instrument excites all the hydrogens at the same time. Some absorb slightly higher amounts of energy, some absorb slightly lower amounts of energy, and then when those hydrogens relax, all that energy is released, and the instrument has to measure it all at the same time. So mathematically, then you have to separate out the smaller amounts of energy emitted from the higher amounts of energy emitted, and it will plot those in a graph. And that's what you'll end up interpreting. So a lot of these details aren't really important to understand. As long as you have a general sense for how things work, then you can do the part that an organic chemist would normally do, which is to take this graph of all the different signals at all the different energies and interpret what it means about the structure of the molecule, which is what we're going to focus most of our time on, and what you'll be more likely to be asked about on exams. A lot of times it might be hit with energy multiple times, and all the energy emitted would be averaged together to give you a greater quantity of signal over the underlying background noise. And typically you prepare your sample neat, which just means it's pure with no solvent. Or if you use a solvent, you'd have to use a special type of solvent. We'll talk about it in a minute. You put that in an NMR tube, which then goes into the instrument. The tube is usually spun at a high rate, and that's just to average out magnetic field variations or tube imperfections, and that's important to get a good signal. So when you have a chance to do an NMR with me in lab, remind me, and I'll let you look down into the instrument where the tube is placed, and you can see when I turn on the air how quickly that tube spins to average out all those imperfections and get the best NMR spectra that you can get with our bottom of the line instrument. But it does meet our needs. So when you need a solvent, so if your sample is a solid and you put a solid into an NMR tube, you won't get a good signal because you're not going to be able to get everything averaged out. You'll get these really broad peaks. So you want to just see the average peaks because not every molecule has the exact same environment at all times. So spinning it around really quickly and keep it in the liquid state is how that's achieved. So the most common NMR solvent is chloroform D. There are others, but the D stands for deuterium. So chloroform is CH3, CHCl3, and chloroform is a good solvent for a lot of organic compounds because it has a slight dipole. Right, the chlorines are more electronegative than the carbon. Carbon's a little more electronegative than the hydrogen. So there's a little bit of a partial positive, partial negative on opposite ends. So it can form some minor dipole-dipole attractions with some compounds, but it's not too polar. So just due to entropy, it will also usually mix thoroughly with a lot of low polarity compounds. So chloroform is a good solvent for a lot of different organic compounds with varying polarities. The problem with having chloroform, though, is that this hydrogen gives a signal. And we'll see a little later, the signal appears in a specific spot, which is 7.26 ppm on the graph that we'll see some examples of in a minute. But if I have a lot of solvent molecules and every one of those has a hydrogen, then this peak I'm going to see for that signal when that hydrogen gets excited and then relaxes and releases energy in this particular energy quantity, this peak is going to be huge because I'm going to have tons of solvent molecules all releasing the same amount of energy. And so I won't see any peaks relative to that for the compound I've dissolved in the chloroform that I'm trying to analyze. So the point of deuterium here, replacing this hydrogen with the deuterium, is to keep basically the same solvent with the same polarity, so it'll still dissolve just as many organic compounds. But now that my solvent doesn't have any hydrogens, it won't produce any signals in the NMR. There is, however, going to be a signal when you use chloroform. You might see a tiny signal at 7.26 because you might have a few molecules that actually do have a hydrogen there instead of deuterium. It's hard to get this 100%. And over time, some of the deuteriums get replaced with hydrogens because hydrogen's more abundant. So you just want to look out for that signal and don't start to think it's part of your compound. If you see it, it's probably more likely to be due to a few hydrogens that got onto your deuterium solvent. But since most of the molecules don't have a hydrogen, the solvent molecules would be invisible, and then the peaks you would see would be due to the hydrogens in the molecules that you're analyzing that you dissolved in the chloroform. And so that answers the first quiz question. Why do we use deuterated solvents in NMR rather than protonated solvents? So why are we using CD3 instead of CHCl3? Why would, if we had a really polar compound that wouldn't dissolve in this low polarity solvent, we might want to use water, but instead of H2O, we would use D2O. We would replace each hydrogen with the deuterium. And the reason for that is because if I use a solvent that has protons, and that's a major component of my sample, I'm going to see massive, huge signals for these hydrogens that are going to make all the other signals look too small for me to really analyze them. So the idea is replacing hydrogen with deuterium retains the same solvent polarity, so it'll still dissolve the same things that would normally dissolve in the solvent. But now my solvent molecules won't produce any signals, so the signals I see should be due to the substance I've dissolved in that solvent that I'm trying to analyze by NMR. Is such a solvent necessary when analyzing carbon NMR? No. So typically we would run carbon NMR and proton NMR. We would run the carbon NMR and proton NMR on the same sample. So if we're going to prepare a sample with the deuterated solvent for proton NMR, we would just use the same sample for carbon NMR. But since we're looking at the carbons, it doesn't matter if our solvent has hydrogens because those signals are not going to show up in a carbon NMR anyway. The carbon NMR is tuned specifically in a different part of the radio wave spectrum, so we only see signals in that part of the spectrum for carbon atoms. If I use a carbon-containing solvent, I will see a peak for any carbon-13s, so I want to be aware of that. But the hydrogens are not going to be a problem. So I don't necessarily need to replace them with deuterium if I'm doing a carbon NMR. So hopefully that makes sense. Any questions about anything so far? Okay, so after you put your sample in the instrument, it puts it in a magnetic field, it hits it with radio wave energy. The hydrogen or carbon atoms change their alignment, and when they relax back down to the lower energy alignment, they release energy, and these signals of energy are then plotted on this graph. So here's an example of an NMR spectrum. There are lots of different types of information you can get from the spectrum. And we're going to talk about each one of these one by one, which is going to carry us through Thursday. So the number of signals is really just the number of distinct types of energy that are absorbed. So I have one signal here absorbing a specific quantity of energy, another signal here absorbing specific quantity of energy, another signal here absorbing specific quantity of energy. So I have 3 signals in this particular NMR. What does that mean? Why do I care how many signals there are? Well, each signal represents a specific type of hydrogen, right? Some hydrogens, so let's, for example, this hydrogen, the hydrogens that are giving this signal, up here, this is the higher energy side. And this is the lower energy side, which we'll talk more about that in a minute. But these hydrogens over here required more energy to excite because they were shielded. That means these are hydrogens that have a fair amount of electron density around them. So that means those hydrogens are probably on a carbon and there's no highly electronegative atom nearby, maybe only carbons or other hydrogens. These ones appear a little bit further down in energy. So that means that they are not quite as shielded with electrons. If they're a little bit down in energy, that means they're de-shielded. They don't require as much energy to excite, and so maybe those hydrogens are on a carbon that is bonded to something electronegative, like an oxygen or something like that, right? So we're going to talk a lot in detail about this, and it's going to hopefully become more clear to you. But the number of signals tells me if I have multiple hydrogens that are all equivalent, they would give one signal. And maybe these 2 hydrogens, because they're on a different carbon, maybe there's an oxygen here or something, they would give a different signal. And the hydrogens down here would give it a different signal because they have a different environment. So we're looking at different types of hydrogens with different environments giving different signals, and that we can start to figure out how to put that together to determine the structure for the molecule. The shift is really the position on the scale. So here this one shifts to about 7.2, this one shifts to about 2.7, here I've got a shift to about 1.2. So the position of the peaks on this part per million scale also gives me information. As we said, the more close the hydrogens are to an electronegative atom, the more de-shielded they are with electron density, so it doesn't take as much energy to excite them, and so we see those appear in a different position on the scale. So we'll learn what typical bonding arrangements give peaks in different positions on the scale. And then on Thursday we're going to talk about integration and splitting patterns. So notice that some of these have 1, 2, 3 signals, or three signal pattern. This one has a 1, 2, 3, 4 signal pattern, and this one looks all weird. It's got a bunch of little signals there. So the way that the peaks appear in terms of whether it's like a single peak or whether it's split into 2 peaks or multiple peaks, that also gives us information about the structure of the molecule, and we're going to talk about how to interpret that on Thursday. So the first major thing we need to deal with is how many signals should appear in the NMR, or if we get an NMR and we see a certain number of signals, what does that tell us about the structure? So first thing we have to recognize is some hydrogens are equivalent, which means they will give the exact same signal. So if this structure here had 3 hydrogens that all have the exact same environment due to the fact that this bond can rotate and they're all equivalent spatially and they have the exact same chemical environment and the same shielding, that means they'll all require the same amount of energy to excite, and when they relax, they'll all release the same amount of energy. So each one of these hydrogens will release some energy, and so that's why I'm getting a bigger peak here, because there's a greater quantity of hydrogens that are all releasing the same amount of energy, and they're all stacking on top of one another and giving the same signal. So one signal often represents multiple hydrogens. And the area of the signal, which is the integration, relates to how many hydrogens are producing that signal. So we have to be able to look at a structure and determine if hydrogens should give the same signal or if they should give different signals. And that's the idea here. If they're homotopic, which means that there's really no difference between them spatially, then they should give the same signal. And so one way to check for that is to look for a rotational axis. So if I imagine this axis and then I rotate the molecule, this hydrogen will flip up and become the other hydrogen. It would take the place of the other hydrogen. This hydrogen would flip underneath and become in that position. And since this methyl group is equal to that one, when one flips up here and the other one flips down there, the molecule looks exactly the same. So if I can rotate the molecule to put one hydrogen in the same position where the other one is, and the molecule looks exactly the same, that means those two hydrogens are rotationally equivalent. And that means they have the same environment, and they'll give one signal instead of multiple signals. Same thing here. If I rotate the structure this way, this hydrogen will come out of the plane and then pop down back into the plane where the other hydrogen was, and this hydrogen would rotate to where that hydrogen is. And the two fluorines will switch positions, but since they're identical, the molecule will look exactly the same after I rotate it, and so rotating it means these two hydrogens are equivalent and they'll give one signal, and the same for those two hydrogens. So looking for a rotational axis is not the same as looking for a mirror plane. If I have a rotational axis, the two hydrogens are equivalent, which means they'll both give signals, but the signals will be identical stacked upon one another, so it will look like one signal. Another test which I recommend you do instead of the rotational one is to do the replacement test. Right? So we said for this structure there's an axis here. If I rotate, this hydrogen can take the place of the other, can rotate up there, and when that happens, the molecule, so if we call this hydrogen 1, this hydrogen 2, the hydrogen 2 would end up here, and hydrogen 1 would end up down here. And so the structure looks exactly the same. So 2 and 1 are equivalent because they can both take each other's place just by flipping the molecule over in space. But the other way to show that they're equivalent is to actually do a replacement test. So in my mind, I replace one hydrogen with a deuterium or some other element, and then I replace the other hydrogen with the deuterium or some other element, and I draw the two resulting structures. Are they the same? Yes, I can flip this one over like a pancake and slide it over, and everything lines up perfectly with the other one. So if they're superimposable and identical, even after replacing the different hydrogens with deuterium atoms, that means those two hydrogens were equivalent to begin with, and they'll only give one signal, and that also means that they're homotopic. So the replacement test is a great way to see if the two hydrogens are really equivalent or not, or whether they give different signals. Just to quickly point out, if I had this structure, and I did the replacement test, let's replace this hydrogen with the deuterium first, and we'll replace the second hydrogen with the deuterium. What's the relationship between these two structures? Well, they're not identical. That means these two hydrogens are not homotopic. They're actually different. One of them is on the same side of the double bond that can't rotate with an ethyl group, and the other is on the same side of the non-rotating double bond with a methyl group. They have slightly different environments, even though they're bonded to the same carbon. And so these two hydrogens would not give the same signal. They would give different signals in the proton NMR. So when I see multiple signals for those two hydrogens, I can verify that it might match the structure because those two hydrogens are not equivalent. These two molecules are not the same. If I flip one over, there's no way to line it directly upon the other one. They are diastereomers in this case. So these two hydrogens are what we call diastereotopic. They are not equivalent, and they would give different signals in the NMR due to having different environments. There's also something called enantiotopic. So enantiotopic hydrogens have a mirror plane of symmetry that splits the molecule in half, right? So here, there's a mirror plane right here, right? This fluorine is in that plane coming out at me, so really what the structure would look like is the fluorine would be here, the fluorine, and the chlorine will be really directly behind it. So when I imagine a mirror plane here, the mirror would split the fluorine atom in half and the chlorine atom in half. So this hydrogen over here is reflecting the other hydrogen. The half of the fluorine is reflecting the other half of the fluorine, half the chlorine is reflecting the other half of the chlorine. So there is a mirror plane here. It's much easier to see if you make a model. But when one half of the structure is the mirror image of the other half, in this particular structure here, when one half of the molecule is a mirror image of the other half, that means the hydrogens have virtually the same environment, so they would give one signal. Over here, my mirror plane is in the plane of the molecule. So the one hydrogen in front of the plane would reflect onto the hydrogen in the back if I put my plane in the plane of the molecule. So that means those two hydrogens are equivalent. So that's difficult to see, which is why I recommend you do the replacement test instead. So if you're looking at the replacement test for this structure, and I replace one hydrogen with the deuterium, and then I replace the other hydrogen with the deuterium, I get two different molecules. What's the relationship between them? They are enantiomers. So when I do the replacement test, not only can I determine whether these hydrogens are equivalent or not, and whether they'll give the same signal or different signals, I can also determine their relationship. If replacing them with deuteriums gave two identical structures, I could say they're homotopic. If replacing one with a deuterium and the other with deuterium gives a pair of molecules that are enantiomers, then I can say they are enantiotopic. Enantiotopic and homotopic hydrogens are equivalent. Right, so because there's a mirror plane here, spatially, this hydrogen has the same environment as that one. And if the only difference between the resulting compounds when I do the replacement test is that they are mirror images, well then their environment of this deuterium is equivalent to the environment of this deuterium, and that means those two hydrogens don't have different spatial environments, and they should give the same signal in the NMR. So these two hydrogens would give one signal, and when I look at the NMR, I'd see one single peak. Both hydrogens would be giving that peak in the same position, so it would just look like one peak for both hydrogens. Alright, so let's take a look at this structure. So we just want to focus on these two hydrogens and figure out whether they're the same or not, whether they're equivalent or not. So let's do the replacement test. So I'll replace one with the deuterium. So let's replace the one with the solid wedge first. And then I'll replace the other with the deuterium. As well. And so what is the relationship between these two? Can they be superimposed? Can I flip one over or rotate something to get them to lie directly on top of one another? No. So that means these hydrogens are not homotopic. Are these two structures superimposable? No. We just said that. Are they mirror images of one another? No, they're not. I can't. If I drew the mirror image of this one, it would not be the same as the other one. If I imagine a mirror plane here, and I flip this molecule over, part of the molecule would reflect, the OH might reflect up here, but actually this area of the structure would reflect this area of the structure if I flipped it over, but the oxygens wouldn't reflect. So if they're non-superimposable, non-mirror images, and the only difference between them is the spatial positioning of the deuterium and the hydrogen, that means they're diastereomers. And so the original two hydrogens are neither homotopic nor are they enantiotopic. They are diastereotopic. And that means their environments are a little bit different. This hydrogen here, spatially, is Gauche to the OH group. 60-degree dihedral angle there. This hydrogen here, spatially, is anti to the OH group. They have different environments. There's no way to rotate this bond enough to make those two hydrogens equivalently spaced from the OH group. So anytime I already have one chiral center and I replace the hydrogen with the deuterium, if it creates a second chiral center, now these two molecules have two chiral centers, and we said they're diastereomers because when one chiral center retains this configuration and the other chiral center here has the opposite configuration, that's how I get diastereomers. To get enantiomers, they'd have to have the opposite configuration at every chiral center. And so if I do the replacement test and I find the hydrogens are not homotopic or enantiotopic and that they produce a pair of diastereomers, meaning that they are enantiotopic, that means they are not equivalent and they will give different signals in the NMR. So the NMR is sensitive enough to tell the slight difference in this hydrogen's environment versus hydrogen, even though they're on the same carbon. And that's really important for us to recognize so that we can match up the peaks we see in the NMR with the peaks we expect to see for the structure, if we want to determine that the NMR represents a specific structure. And so that's the idea here. Here are some shortcuts you can take a look at. So one thing is, if I have a carbon with three hydrogens on it, there really shouldn't be any exceptions to this. No matter what that carbon is bonded to, those three hydrogens should all be equivalent. So no matter what this methyl group is bonded to, there should be rotation possibilities here. So three atoms rotating around are going to be spatially equivalent. So those three atoms will be homotopic and they'll give one signal. So the question is when I have a CH2 group. If I have a CH2 group and I'm interested in those two hydrogens, even though they're on the same carbon, they might not be equivalent. So the shortcut you can kind of take here is typically if the two hydrogens on the carbon, if in the rest of the structure there's no chiral centers, then those two hydrogens are usually equivalent. Right? So I really would do the replacement test here to be sure, but since there's no chiral centers anywhere in this structure, I can expect this hydrogen, which is pointing up on top of the molecule, to have the same environment on the top of the molecule that this one hydrogen has below on the bottom of the molecule, because the molecule is symmetrical. The top and the bottom faces are the same, so hydrogen pointing up, hydrogen pointing down would be the same. And so these two hydrogens would give one signal due to being chemically equivalent. If there's a chiral center anywhere in the structure, though, it doesn't even have to be the very next carbon over. If there's a chiral center in the structure, that creates diastereotopic hydrogens. And so that's the second rule here. If there are two hydrogens on the same carbon and there's a chiral center anywhere else in the molecule, those two hydrogens are usually not equivalent and they would give distinct signals. So this one would absorb a slightly different amount of energy than the other one, and so they would then release that energy at different wavelengths and give two different signals with different shifts. One would be Gaussian OH and the other would be anti to the OH. So their environments are different, and they give different signals. We already said this one. If I have three hydrogens on the same carbon, that's a methyl group. All three of those hydrogens should be equivalent. And then the other thing is you want to look for overall symmetry in the structure. So in this case, because I've got two methyl groups on either side here, that means there's a mirror plane here where the left and right sides are equivalent, which means all four of these hydrogens are equivalent. So even though these two are on one carbon and these two are on a different carbon, because they have the same environments, they would all give signals in the exact same position. And so I would see one signal for these four hydrogens, and then the other signals here on the methyl groups, I would see one signal for all six of these hydrogens. So two total signals in the NMR. So the number of signals you see doesn't necessarily tell you the exact number of hydrogens. It tells you the number of unique groups of hydrogens. And when groups are equivalent spatially, because they have the same environment, they'll all give the same signal. So this signal would result from six hydrogens all being identical or equivalent, and the second signal would result from those four being equivalent. Alright, so let's do a little practice with this idea. How many signals should my molecule give? So when I take the NMR of it, I can match those signals up with where they should be based on my predictions from the structure. So here, if I'm looking at the proton NMR, which is what we're talking about now, I want to draw my protons in. So another situation where if you don't draw the hydrogens in, it's going to be difficult to correctly determine how many signals you'll get. So in this structure, I've got a lot of different hydrogens, and I want to label them A, B, C, D, etc. to figure out how many signals I have. So if we're looking at those rules we talked about, all three hydrogens on a methyl group should be equivalent to one another. If there were symmetry in the structure, like something like this, and I had different methyl groups that were spatially equivalent to one another, then all of those hydrogens would all be equivalent to one another. There'll only be one signal in this dimethyl ether because all six hydrogens are equivalent. So is there any other equivalent hydrogens to these ones? No. These are the only hydrogens in this structure on a carbon that's directly bonded to the oxygen, except this one here. And clearly the CH3 and CHs are different. They're not the same because they have different branching and environments. So these three would give hydrogen A, one signal for all three of them. We could call these B. These three would all give one signal. There's nothing equivalent to there. The only other methyl group here is over here or over there, and those are different distances from the oxygen from this one, so clearly they have different environments and would give different signals in different positions on the spectra. This would be a unique hydrogen. It's the only hydrogen on a CH carbon that's directly bonded to an oxygen, so its environment is unique. And then these methyl hydrogens over here are all equivalent because they're all on the same carbon. What about these two hydrogens? Well, if I do the replacement test, I replace one with the deuterium, and then I do this same thing but replace the other with the deuterium. What's the relationship between those two? Well, they're diastereomers. I have two chiral centers. They have the same configuration at chiral center 1, but they have the opposite configuration at chiral center 2. So some of the chiral centers have the same configuration and some are different, that means they're diastereomers, which means these two hydrogens are diastereotopic in relation to one another, and they are not equivalent. Spatially, they do not have the same environments, and so I could call this one E and this one F, which means I have 1, 2, 3, 4, 5, 6 signals that I expect to see in the NMR. Let's take a look at the second structure here. So here I want to draw all the hydrogens in, just like the last example. And when I do that, I'll see there are a lot of hydrogens, so potentially a lot of signals, but then again, if some of the hydrogens are equivalent, they'll give signals in the same position. It'll just look like one signal. So what I want to do here is to count my carbons. Right, so I could call this carbon with the CO double bond attached, I could call that carbon 1. Actually, let's just number from the side. 1, 2, 3, 4, 5, 6, 7. So there are 3 carbons on the left of this CO double bond, and 1, 2, 3 carbons on the right of it. And so that creates a symmetry. So it's not currently rotated in a way that makes it look symmetrical, but we got to keep in mind all these sigma bonds are freely rotating for the most part. So there will be rotations where these 3 carbons over here are equivalent to these 3 over here. And there is a symmetry there. Right? So I could draw it like this if I wanted. And I would see that this position is equivalent to that position, this position is equivalent to that, and this is spatially equivalent to that. So the environments of carbons 1 are equivalent, which means that the environments of the hydrogens on those carbons are equivalent. So this is a situation where these 3 hydrogens are all equivalent to one another, as well as these 3. So all 6 hydrogens A would give 1 signal. And these 2 are equivalent to these 2. So all 4 hydrogens of type B are equivalent, and then all 4 hydrogens of type C are equivalent. So that molecule, even though it has a lot of hydrogens, would only give 3 distinct signals in the proton NMR due to the symmetry of the structure, creating a situation where a lot of the hydrogens are equivalent to one another. So we could mention briefly on a cyclohexane ring. We talked about cyclohexane a number of times. We said the axial positions are different from the equatorial positions. So since I have 6 hydrogens of type A and 6 hydrogens of type B, I would expect to maybe get 2 signals. Do the axial and equatorial protons have different environments? Yes. The equatorial ones are not involving much steric hindrance. The axial ones kind of crowd each other out. In those positions, there's a little steric hindrance, so they're not quite as stable. So yeah, they totally have different environments. And if I were to place a hydrogen in the axial position versus an equatorial hydrogen with the deuterium, I would see that I would get differences. The structures would not be the same. So how many signals would I expect to see in the NMR? I might expect to see 2 signals. But I might also expect to see 1 signal. So why is that? Well, it really does depend on the temperature, but at room temperature, there's enough energy for the ring to flip, to freely flip. So if the feet of the ring come up and the head pops down, and we do a standard cyclohexane chair ring flip, well then all the axial hydrogens in red, I'm just going to draw those ones in, I'll leave the other ones out, would become equatorial. So since they're only axial half the time and equatorial the other half, that all averages out. As long as the ring flipping is occurring faster than the NMR experiment, well then on average, all the hydrogens of type A are equivalent to the hydrogens of type B, and that's when I get 1 signal. So you want to be careful if there's equivalences due to rotation of bonds. Typically that occurs faster than the NMR experiment, so you just see the average signals. Even if the hydrogens look non-equivalent in one structure, if on average they're equivalent due to rotation, they should give the same signal. Right, so that's what we see here. The hydrogen of the axial type becomes equatorial, the hydrogen of the equatorial type becomes axial. As long as that flips back and forth faster than the NMR experiment, then those both will average out to give the same signal. If the temperature is lowered way down to the point where there's not enough kinetic energy around for this ring flip to occur, then you end up with the situation where if the ring flip only happens once in a great while because there's not enough energy to overcome the activation energy barrier when you're going through the boat or the boat twist or a flat structure, any part of the ring, which is higher in energy, the energy is not necessarily around to do that, then you would see two different signals in the NMR, and you can do that experiment. If you have an NMR instrument that has temperature control, if you lower the temperature down enough, you can see two distinct signals for cyclohexane, where normally you would only see one signal at room temperature, which is kind of interesting. All right, so let's take a look at the second quiz question here. How many signals do we expect to get here, and why are enantiotopic protons equivalent where diastereotopic protons are not? So to determine the number of signals, we definitely want to start by drawing hydrogens. No hydrogen on this carbon, it's already got 4 bonds, but there would be one here, there'd be 2 here, there'd be 1 here, and there'd be some here. So this molecule overall doesn't have much symmetry, right? The molecule we talked about on the other slide that looked like this, we clearly see the left and the right sides were symmetrical. So we recognize that some of these hydrogens on one side were equivalent to the ones on the other side due to that symmetry. This structure doesn't really have any symmetry though. The only area where I see potential symmetry is over here. This methyl group looks symmetrical to this one. But that would only be true if this pi bond could rotate, which it cannot. Right? This methyl group up here is sterically close to the CH2. This methyl group down here is sterically close to this hydrogen. There's a difference there. And that difference is locked in place as long as this pi bond can't rotate. So unless we raise the temperature way up to the point where we can continually be breaking and reforming this pi bond in a relatively fast time frame, we're not going to see any rotation here, which means these two methyl groups are not equivalent. So I can call this one, the hydrogens here would all give one signal. The hydrogens here, I'll call these HB. Those will all give a different signal. This hydrogen here is clearly unique. Call it HC. It's the only one in an sp2 hybridized carbon. This hydrogen here is clearly unique. Call that D. It's the only one on the same carbon the chlorine's on. These are equivalent to one another, because if I replace any one with the deuterium, I get the same structure as if I replaced any other one on this carbon with the deuterium because of the rotational averaging of their positions in space. And then here, what we're seeing again is another example of two diastereotopic hydrogens. So these two hydrogens are diastereotopic. Why are they not equivalent? Well, there's a spatial difference between them. Right? So we'll call this one F and this one G. Hydrogen G is Gauss to the chlorine. It's pointing out at me just like the chlorine. They're on the same side of the structure spatially. Even if I rotate the structure around, there's going to be a difference. So let's just explore that. Let's rotate this around. So I'll keep this left-hand side of the structure the same. And we'll rotate this bond. So maybe I want to put the chlorine underneath. So if I rotate the chlorine under, so it has a dashed wedge, that's going to bring this methyl group forward. And this hydrogen would end up being in the plane. So it was these two hydrogens that we're interested in. We'll call this one still G and F. So what we see here is G's environment is a little bit different from F. So this bond can rotate, but G has a different spatial relationship to the chlorine and this methyl group, and F has a specific relationship to this hydrogen and the methyl group that's different. Right? If I'm going to put the chlorine gauche to hydrogen G and look at where the other groups are located, there's a difference from when I put the chlorine gauche to hydrogen F and look at the location of the other groups. So spatially, there's just no way to show that G and F have the same spatial environments, and that's what makes them different. So diastereotopic protons have different spatial environments and will give different signals. They might be pretty similar, right? So it's still the same number of bonds away from the chlorine, same number of bonds away from the double bond when I look at G versus F. So their environments might be similar, and so they might give peaks in very, very close positions and release similar amounts of energy and give similar signals, but they won't be exactly the same unless they have the exact same environment. So that gives me a total of 7 signals, A through G. And these diastereotopic protons are not equivalent due to the specific spatial arrangement at this chiral center. That makes the spatial arrangement of G and F different from one another. If I drew a similar structure, maybe drew it like this. So instead of the chlorine here, I just have another methyl group. Well, this molecule does not have a chiral center. So if I'm looking at these two hydrogens in this situation, you might say, well, this one's gouged to this methyl group. But here, if I rotate the bond and redraw the structure after the rotation, what I see is, when this methyl group rotates back to the dashed wedge, the other one, when this one here rotates into the dashed wedge, the other one will rotate into the plane. So in this case, in one rotation, the forward hydrogen is gouged to the methyl group, and the other methyl group's in the plane. In the other rotation, the backward hydrogen is gouged to the methyl group, and this other methyl group's in the plane. So that does mean that they are equivalent. So when I have enantiotopic protons, which is what these two hydrogens are, because there's no chiral center already, that means they will have the same environment. They'll have the same average environment, which means they'll give the same signal. So you really have to be careful about whether there's already a chiral center in the structure or whether there isn't, to determine whether two hydrogens on the same carbon are equivalent like these enantiotopic hydrogens are, or whether they're not equivalent due to being diastereotopic. Any questions about that? Alright, so that is the rundown on how to determine how many signals there are in your structure. And so now we want to talk about where those signals appear on the NMR scale. So the specific positioning of the signals, so if we look at the scale, it goes roughly from 0 to 12. And the units ppm don't really have much meaning, which is rare for chemistry. The ppm units don't really tell us much. We're really more just concerned with where on this scale from 0 to 12 these peaks appear. And one way to know that is by comparing them to the position of the hydrogens in this molecule, tetramethylsilane. Tetramethylsilane, or TMS, is what's known as an internal standard, or really it's a standard in general, but often it's used as an internal standard. So in most NMR solvents, there's a tiny bit of TMS added to the solvent. And since the TMS has 12 hydrogens, that are all equivalent, all absorbing this very specific quantity of energy and then releasing a very exact amount of energy, that amount of energy, when it's plotted on the scale, can be set to right at 0. So when you see a peak right at 0, that usually is TMS. This standard is often added to your sample so that the instrument or operator of the instrument knows to put that peak at 0, and then other peaks will appear somewhere relative to that position. If I don't have the TMS in there and I just see these peaks, the computer won't necessarily know exactly where to place them unless the instrument has been very recently calibrated. So when we do your samples for Lab 7, or even for the product that you made in Lab 6, you might notice me looking through a little orange book to figure out where your signals should appear. And that's because the instrument doesn't really know exactly where they should appear. And if there's no TMS in your sample, because we're analyzing it in its pure state, these peaks they will appear at the right distance from one another, but the whole thing might be shifted down or up a little bit. Without the TMS to set everything straight, I have to know where one of those peaks goes so I can set it to a certain position, and then the other ones will necessarily be correctly set in their position relative to the one that we've determined. So the units ppm, which is also given with this symbol, the delta symbol here, those units basically come from where the shift appears relative to the TMS signal that we always set to 0. And so, for example, if I have benzene, whichever NMR instrument I analyze benzene, what I notice here is there's a symmetry to this 6-membered ring. So all 6 hydrogens have the same average environment. If I replace any one of them with deuterium, I'd get the same structure as if I replace any other one with deuterium. So they're all homotopic with respect to one another. And they all give one signal. And that signal happens to appear at 7.27. So wherever 7.27 is on the scale, I would see that signal. If I take the TMS and set it to 0, without the TMS, that signal might appear somewhere a little bit off. But if the TMS is present, I know that that's meant to be at 0 because that's the standard. And so when I set that to 0, the benzene peaks always come at 7.27, regardless of the strength of the instrument. Right? So even a lower energy or a weaker magnetic field instrument, I still get the same positioning for benzene. So the way this calculation is set up, we're not going to get into the details of it, but the way it's set up, it allows whichever instrument I use, I should always get the same position for the same compounds. So we can always talk about, making sure that when we're analyzing compounds, we see the signals where we expect to see them, because they should always be in the same place for the same compounds. Notice that the Hertz units cancel, and so really this is basically a unitless value, but because we like units so much, we usually just put some units in there, even though they don't really have any meaning. So I won't ask you about the meaning of the ppm units. You won't have to do any calculations with those units. Really, it's the positioning on this scale that gives us information about the structure, right? So if a hydrogen atom absorbs and releases energy on one side of the scale versus the other, that tells us about the magnetic or electronic environment of that hydrogen atom in the molecule. So when we're talking about where to expect the hydrogens peak, this brings us back to a topic we talked about earlier today, which is shielding. And we said if it's shielded with electrons, meaning that the nucleus has lots of electron density around it, then the magnetic field won't have as much of an impact on it. And that gives me a smaller energy difference between the alpha and beta magnetic alignment states. And so when a smaller energy or lower energy radio wave hits that, it will be absorbed and then re-released. If the higher energy wavelength of light hits that proton, nothing will happen, right? So this is a quantized situation. Only certain quantities of energy will do the excitation and will be then released and measured. But it depends a lot on the shielding of the atom, as we've been saying. The more electron density there is around that nucleus, the smaller the energy difference between the two magnetic alignments and the smaller quantity of energy released. I think I may have misspoken earlier and mixed that up a little bit. Now that I'm thinking about it, I apologize for that, but this is correct here. So let's make sure we clarify exactly what's happening here. So this sometimes gets confused in my mind, and it happens a lot for students as well, not surprisingly, because it's a little bit confusing with the way the terminology is used, but it results from the fact that the way these instruments have been designed over the years has changed. So in the early days of NMR, what they would do is they would use only one energy to excite the atoms, and then they would modify the strength of the magnetic field. So as we're saying, if I have a strong magnetic field, then I'm going to have a larger energy gap. If I have a weak field, then I have a smaller energy gap. So if I'm only using one constant energy, some of these hydrogens would naturally have a larger gap than others. In order to get that energy to be absorbed and then re-released by that hydrogen, I have to increase or decrease the strength of the magnetic field until the magnetic field matches the energy gap for the atom, and then that energy is absorbed and re-released. But probably for reasons that are obvious to you now, because that's a confusing way to explain it, that design for the instruments is no longer really in use. So what we do instead is to use a constant magnetic field strength. So one magnet is in your instrument and it's holding the atoms in a specific magnetic field with a specific strength. And then all the energies are shined at the sample, and some of those energies absorbed and some are not. And so the energies that are absorbed are then re-released, and that's where I get these signals. So the higher energy side is actually here on the downfield side. Downfield refers to lower strength of the magnet. And that's a holdover from the earlier way of running NMR instruments. But unfortunately, chemists use this terminology a lot, and it's caused a lot of confusion for myself over the years as well. Downfield, confusingly, refers to higher energy, greater ppm values. And that's de-shielded proton. Right? So if you can remember that when the hydrogen is somewhere close to an electronegative atom, and that attracts electrons away and creates a partial positive, there's not much electron density around there. So there's nothing shielding the magnet. And so the magnet creates, even though the magnetic field strength isn't changing, for that hydrogen, since it's not shielded from the field strength of the magnet, it will have a relatively large energy gap. And that will shift it toward the higher energy side of the spectra, which is inconveniently called downfield. And so that's what we see de-shielded protons. So we're going to see here in a couple minutes how, depending on what elements are attached, the effect that they have on the nearby hydrogen, that will cause the hydrogen signal to appear more upfield or more downfield. It will be lower quantities of energy required to excite it because the field strength won't cause such a high energy gap, or it'll be higher energy of radio waves required to excite it because it'll be more exposed. The magnet will cause its energy gap to be larger, and so larger quantities of energy will be absorbed and then re-released. So let me just go back to where I said the wrong thing and clarify that. Yeah, I was on the slide earlier. So sometimes my brain switches this up for me. So just want to make sure we understand. If it's shielded, because there's a lot of electron density around it, that means it's shielded from the magnetic field. And if the magnetic field doesn't affect it as much, I get a smaller energy gap. And so there's less energy absorbed to excite that nucleus, and thus less energy released when it relaxes back down to its lower energy alignment with the magnetic field. And that smaller quantity of energy appears upfield on the lower energy side of the spectrum, which is closer to 0 ppm rather than the higher energy side, which would be around 12 ppm. So I apologize for mixing that up, and hopefully that doesn't create too much extra confusion beyond the normal confusion associated with this content. So let's look at some numbers and some specific examples. If I take a look at methane, it comes right around 1 ppm, right? So these hydrogens, 1 ppm, these hydrogens are not really de-shielded. The carbon-hydrogen electronegativity difference is very minimal, so the electron density is pretty well shared over both of them. And when it's shielded from the magnetic field, I get a small energy gap, right? The stronger the magnetic field, the more it affects the atom, the bigger the energy gap. So with the small energy gap, that comes on the upfield, low energy side of the spectrum. If I put a more electronegative atom there that affects the carbon, or even a little bit more electronegative, or even more, or even more, that causes the carbon to attract some of the electron density proportionally from the hydrogen. And so these hydrogens are de-shielded. They don't have as much electron density because they're pulled away through induction by these more electronegative atoms. So when they're de-shielded, the magnet affects their nucleus more. There's a bigger difference between when the magnetic field of the hydrogen aligns with or against the magnetic field of the instrument, if there isn't electrons shielding the atom from that magnetic field. So here I would get a larger energy gap, and when more energy is required to excite that, that would be downfield on the higher energy side, which is what we see here around 4.3 versus 1.0. And if I put, for example, multiple electronegative atoms on there, each one of those de-shields the hydrogen a little bit more, pulling electron density away, and that causes the hydrogen to then have an even larger energy gap, which requires higher amounts of energy to excite, and then higher amounts of energy are released once it relaxes back down. In this structure here, you can see how proximity to the highly electronegative atom really affects the positioning of the peaks, or the shift. So if the hydrogens are very close to the electronegative atom, they're quite strongly affected. Once I get one atom away, there's really a minimal effect, and then two atoms away, the effect is virtually nothing. So typically a CH3 comes right around 1 anyway. And so these ones are far enough away from the chlorine where as it's pulling electrons to create a partial positive, and that tries to pull electrons to create a little bit of partial positive, the ability of that to pull electrons is pretty minimal. So diminishing effect of electronegative atoms. They really only affect the atoms that are within 1 or 2 atoms away. After that, we don't have to worry about how much they affect the shift or positioning of the peaks, or the energy, or the degree to which the hydrogens are shielded or de-shielded. So that's convenient. At least we only have to worry about how electronegative atoms affect the structure and the hydrogens when they're 1 or 2 atoms away. Also, it turns out that the number of hydrogens on a carbon affects shielding and de-shielding a little bit. So we're not going to get into too much detail here, but these are values. These are like baseline values. If I have a methyl group, it's going to be around 0.9 or around 1 ppm, unless there's something electronegative here to pull electrons away and de-shield. So if there's no highly electronegative atoms nearby to cause de-shielding, this is the baseline. This is where I normally see hydrogens on a methyl group. A methylene is a term that describes a carbon with 2 bonds to who knows what and 2 hydrogens. And those, when I have a methylene, the hydrogens appear around 1.2 as their baseline, unless there's something electronegative to de-shield them and cause them to be shifted to an even higher energy position on the spectrum. And then if your hydrogen's bonded to 1 carbon, or if the carbon only has 1 hydrogen and the other things bonded are carbons, or maybe something even more electronegative, but if they're carbons specifically, then I usually see that around 1.7. So the nature of the carbon, whether it's a methyl, methylene, or methine, does have an impact as well on the positioning of the atom. So what the textbook describes is, if you have hydrogens and you're trying to predict where on the spectrum between 12 and 0 is this peak going to occur, first thing you want to look at is, if you're trying to determine the peak for a hydrogen, how many other hydrogens versus carbon groups are bonded to that. Is it a methyl group? Is it a methylene or a methine? And then we'll look at how much that baseline value is affected or shifted even further downfield if there's an electronegative element nearby. And so that's what we can take a look at. So typically we'll look at a variety of molecules and some of the trends that we can pull out from looking at a lot of different molecules. One trend is, if there's an oxygen directly attached to the carbon, that's going to affect the shift of these hydrogens by about 2.5 to 3 ppm. That is the amount of de-shielding that an oxygen does to affect the magnetic field of the hydrogens that are on the very next carbon over. So we're not talking about 2 carbons over. We're also not talking about the hydrogen that's directly bonded to an oxygen, which we'll talk about in a little while. We're just talking about hydrogens on carbons for now. So the hydrogen that's on a carbon, if there's an oxygen on the same carbon, then we would start with the baseline of 1.2 because these are methylenes. And then we would add 2.5 or 3. And if I'm asking you to predict these shifts, they don't have to be exact. Anything close to 4 ppm would be reasonable. So you can add, for an oxygen that's directly bonded to the same carbon the hydrogens are on, if you're looking at the shift for those hydrogens, if you start with where hydrogen for methylene normally occurs and add 2.5 or 3, that'll put you right around 3.5 to 4 ppm. That's totally fine. That's close enough. We just want to get roughly in the right range for where they should be if I'm asking you to predict where the shifts will occur. If you have a hydrogen on a carbon and the very next carbon over has a CO double bond, a CO double bond is it causes a big electronegativity difference. And those electrons shift a lot. And that creates a big partial positive right here. So it's not creating the partial positive on the same carbon that the hydrogens are on, right? That's what we saw over here. When the oxygen is right on that carbon, it creates a big partial positive there, and these hydrogens are de-shielded, and so they cause a significant shift, a big shift. If the oxygen's one more carbon away, the electronegativity differences will still pull some electrons away, but not as much because it's an extra atom distance. And so that usually causes a shift of only about 1. So if I start with the baseline for methylene and add 1, I can predict where the peak would be for these hydrogens, somewhere around 2. And so again, you don't have to be exactly perfect. So we're just making predictions. We'll just want you to get roughly in the correct range. So let's make some predictions here. Let's use all the information we talked about today to predict the number of signals as well as the shifts for the signals. So in terms of the number of signals, we want to draw the hydrogens in. There'd be one here. There'd be a couple here. And that's it. So how many signals should I see? Well, these three will all be equivalent, so we'll call these three HA. They're equivalent to one another due to the rotation of this bond. This hydrogen is unique. It's the only one bonded directly to an oxygen. This hydrogen is unique. And what about these two? Well, I have a chiral center. That makes these two hydrogens diastereotopic. They're not spatially equivalent. So even though the chiral center isn't the next center over, it still creates a situation where if I were to replace this hydrogen here with the deuterium, I would get a different diastereomer versus if I were to replace this hydrogen with the deuterium. So these two hydrogens are not equivalent. So let's call one D and the other E. So we should see 5 signals here in the NMR. So let's list those. Now let's try to predict where the shifts would occur. So HA is a methyl. So if we go back here and look at methyl, normally come around 0.9. And we don't have to be perfect. So if you want to round that up to 1, that's fine, but we'll just start with 0.9. What's directly attached here is another carbon. There isn't an oxygen directly attached here. If there was, I would add 2.5 or 3 to that. But there's an oxygen 2 atoms away. So I'm probably going to add about 1 to that. And so that's going to appear somewhere around 2 on the spectrum. Hydrogen B is very difficult to predict its position. So you're probably thinking, well, if it's directly attached to an oxygen, there's a big electronegativity difference there. The hydrogen should be very d-shielded, and it should be quite far downfield. That may be the case, but due to hydrogen bonding, if another molecule brings something around with a lot of partial negative, that electron density could also shield the hydrogen. So it's really hard to say how shielded or de-shielded this hydrogen is. So we're going to say for any hydrogen that's directly bonded to an oxygen, it's very difficult to predict. It really could be anywhere between usually around 2 and it could be upwards of 8 or 9 ppm. And that's almost the whole scale. So I don't expect you to accurately be able to predict where an OH hydrogen appears. In terms of hydrogen C is a methine. It's on a carbon with no other hydrogens. So if it's on a carbon, it's going to be one of these 3 types. If it's a methine, I would start at 1.7 and move up from there. So I would start at 1.7 and I would add to that. So this hydrogen is on a carbon that has an oxygen directly attached. So I'm going to add 2.5 to 3. It's also 1 away from this carbon with an oxygen. So this hydrogen C is on a carbon with an oxygen directly attached, and there's another oxygen not directly attached, but 1 more carbon out. So that means I should add another 1. Right? So this 2.5 is added because of this oxygen directly attached to the same carbon the hydrogen's on, and the 1 is added because of the extra carbon here that has an oxygen, a CO double bond. So if I add that all up, I'm going to get about 5 to 6 ppm. And so the signal for HC should be further downfield than the signal for HA for sure. Doing the analysis for D and E, I'll find I get the same result. So even though they're not equivalent and they will give different signals, those signals should be close to one another. When I look at D and E, they're on a carbon. So D and E are both on a methine, right? There's a CH2 here, and when I have a CH2, that starts at 1.2. So for each of those, I would start at 1.2, and I would add something to that. So if I've got this carbon here and this carbon here, what's directly attached to this carbon is 2 carbons. So there's nothing highly electronegative that's directly attached to this carbon, so I'm not going to see a major shift away from 1.2. But the next carbon over has a CO double bond, and on this side the next carbon over has some chlorines. So all that electronegativity is pulling electrons away, and that's going to pull these electrons away, and it's going to de-shield these hydrogens. So probably I would add maybe 1 to 2, maybe add 1 for the CO double bond and 1 for the chlorines there. So I expect this one to be maybe around 3 ppm. And that would be true for hydrogen D and E. They would be a little bit different from one another, but they would both be relatively close to 3 ppm. So in this structure, I should see one signal around 2, 2 different signals around 3, 1 signal around 5 or 6, and then another signal somewhere for the OH that's would appear, but it's hard to predict exactly where it would be. And if I saw all those signals in the NMR, once I'm analyzing the sample, I could probably confirm that the NMR matches this structure, and that tells me maybe I was trying to make this structure with some kind of synthesis. It tells me that my synthesis was successful. When you have an aromatic ring, things get a little weird. So the fact that there's resonance here, and if I look at what the resonance hybrid looks like, the electrons in this pi cloud, the molecular orbital that extends over all 6 atoms due to the resonance, those electrons create something called diamagnetic anisotropy, which means there are different areas of the structure that have different magnetic environments. So when a hydrogen is pointing away from that cloud, due to the way the cloud interacts with the external magnetic field, these hydrogens end up appearing as if they're highly de-shielded. They're not really de-shielded because there's no electronegative atom pulling electrons away, but what happens is the electrons in resonance here will add to the extent to which the external magnetic field affects this hydrogen. So we're not really de-shielding the hydrogen and exposing it to the magnetic field, but this ring kind of amplifies the effect the magnetic field has on this hydrogen. And so it acts as if it's de-shielded, and that's why we typically see hydrogens on aromatic rings usually between 6 and 9 ppm. So that's pretty far downfield, pretty far to the high energy side due to that aromatic ring. So here is the original NMR that we first looked at today. It was ethylbenzene. These 5 hydrogens are giving this signal down here in the aromatic region. These 2 hydrogens here giving this signal, and these 3 hydrogens here giving this signal here. So the hydrogens on the ethyl group here are not really very de-shielded, so they appear in the standard areas. The one here, these 2 hydrogens relatively close to the ring are de-shielded, or at least act as if they're de-shielded by the ring a little bit. But the hydrogens that are directly on the ring are really affected by the resonance of the ring, amplifying the degree to which the magnetic field affects them. And so there are larger energy gaps, and when they absorb and release energy, I see those signals in a higher energy part of the spectrum. Why I'm only getting one signal for all 5 hydrogens, even though some of them are homotopic and some are not equivalent, well, their environments are pretty similar, so their signals are kind of overlapping. So I get one kind of conglomeration of each of those individual signals, and there's lots of individual peaks there, and so that's kind of called a multiplayer. We'll talk more about that on Thursday. But when you have multiple hydrogens that are very similar, and they all appear not exactly in the same spot, but overlapping one another, I get this peak, and I can't determine the pattern there. Like this is a pretty clear pattern of 4 signals, a clear pattern of 3 signals, but this is a mess. So that happens when I have multiple hydrogens that are not exactly the same, but very similar. So the key here, though, is to recognize aromatic hydrogens directly attached to an aromatic ring. So we're not talking about hydrogens on a cyclohexane. If I don't have the resonance, then I don't have the diamagnetic anisotropy. If there's no resonance, the hydrogens are not deshielded by anything. These hydrogens would appear probably around 1.5. They go all the way down here around 6 to 9 because of the pi bonds and the resonance there affecting how strongly the hydrogens feel the external magnetic field. So make sure you look out for aromatic hydrogen. So this is a crazy structure. It's called 14-annuline. When I look at the NMR of 14-annuline, I see 2 signals. One occurs at 8 ppm, which is very high energy side of the spectrum, and one occurs at -1 ppm. This is a very low energy side of the spectrum, even lower than the TMS standard. So which hydrogens are which? Well, what we see here is there's resonance all the way around this ring. These electrons can shift all the way around, which means that in reality, the electrons exist in a molecular orbital that extends all the way around the structure. And that circulating electron density magnifies the electrons, it magnifies the degree to which the magnetic field affects some of these hydrogens. And it's going to be these hydrogens on the outside. Right, these hydrogens on the outside are very similar to the hydrogens on an aromatic ring. They're not covered by the electron density, but the circulating electron density does magnify the effect that the magnetic field has on those hydrogens. So those hydrogens appear downfield around 6 to 9 ppm. The hydrogens in the center here, though, they're covered by that electron cloud, so they're quite shielded. So these ones are the ones that have extra shielding. So if I could get a hydrogen covered, like somehow there was a hydrogen in the middle of the ring, which that wouldn't be possible, but if I could get a hydrogen covered by the electron cloud, shielded by it, then the magnetic field would have a minimal effect on it, and the energy gap would be very small. So I would see that signal in the low energy side of the spectrum. And that's basically what we're talking about here. These hydrogens are shielded by the cloud. If the hydrogens are on the outside of the ring, they're not really shielded by the cloud because the cloud only covers this part of the ring, but they are going to be impacted by the interaction between the electron cloud and the magnetic field, and that increases the energy that they absorb and release in the NMR experiment. So overall, here are some trends, and a lot of this is on your formula sheet in a slightly different form, so you'll definitely want to be working intimately with your formula sheet when you're practicing these problems so you can get used to using it. But again, depending on the environment of the hydrogen, that determines where the signal appears. If it's close to an electronegative halogen or close to an oxygen, it could appear really in a variety of different positions. If it's on a ring, that affects its positioning. If it's on a sp2 hybridized carbon, that will affect its positioning. And so, reference these tables and the formula sheet as you're practicing these, and then you'll just start to get used to seeing the patterns and where different hydrogens that are bonded in different ways appear differently in the spectrum. Any questions about anything today? We're definitely going to do more work with that and lots of practice later in the week. But in the meantime, highly recommend you practice some of these. A lot of students have trouble with NMR, and one of the reasons is because NMR is very detailed. You get a number of signals. Each signal is in a certain position on the spectrum. Each signal may be splitting in some way, and you have integration. So there's a lot of information there, and it takes a lot of practice to really master it. So next time we're going to do some practice. So these videos will be helpful, and we should be able to finish off chapter 16 and complete our discussion of NMR spectroscopy. And in the process we'll do some examples, but obviously we only have so much time in these lectures, and I always go over time anyway. So definitely do as much practice as you can. Let me know when you have questions, and we'll take it from there. So that is it for the formal lecture, and feel free to type any questions or anything that you Oh, Amy has a great question about significant figures. So you do not have to worry about significant figures when it comes to calculating chemical shift. Probably whole numbers are reasonable. If you're observing chemical shift for a spectrum, like here, so you would find, just here. So if I give you a spectrum and I ask you to report the chemical shift, you just kind of eyeball where the middle of the signal is, and then you can estimate one sig fig. So this would be around 2.6. Estimate one decimal place. I mean, not one sig fig, sorry. Estimate one decimal place, that's fine. If you're using this system here, where you're estimating from the structure, if I give you a structure and ask you to estimate where the signal should appear, in that case, one sig fig would be adequate, and even beyond that, estimating in a range of values like we did over here. For this structure, we said, for example, this hydrogen might, right here, it might come somewhere between 5 and 6 ppm. So you don't even need to give an exact number, let alone worry about the sig fig. So if I give you a structure, start with the type of bonding arrangement, whether it's a methyl, methylene in this case, or methine. Start with that ppm, and then look at what's around. If you have to add 1 or 2 to get a value, the sig figs associated with that value I wouldn't be looking at, because it's all an estimation anyway. So we could say, maybe this is somewhere between 3 and 4, or even if you just said around 3, you can put an estimation symbol there to indicate that it's just an estimate anyway. So if you're estimating from a structure, you don't have to worry about sig figs. If you're determining where the peak is from a spectrum, then I would usually expect 1 decimal place, because you can at least eyeball 1 decimal place for where the center of that peak is positioned. Good question. Any other questions about anything? You're welcome, Amy. All right, well, if you do have any other questions, feel free to stay on for a little while. I'm going to stop sharing, but I'll be here if you do want to speak up, we can discuss any other issues that you might have questions about.